So it's actually a pretty easy program to use. You build models like this. Do you know what this is? Black is carbon, red is oxygen. This is carbon monoxide. Carbon oxygen triple bond. And then I sent this off for some quantum mechanical calculations, which I did, and then I want to just display the electrostatic potential map. So I calculated that. This is the electrostatic potential map here. It's not that polar, carbon monoxide. Yeah. This end's getting more positive here. What's that end? The carbon. Not more positive, more negative, I should say, more red. What we can do is we can look at the charges on these. Let's take a look at the charge on this carbon. Electrostatic charge is slightly negative here. The charge on the oxygen, slightly positive. That's carbon monoxide. Let's continue on. Other questions? You'll be asked about distorted angles too. Do you know the rules for distorted angles?
On the test, how are you supposed to find out what the angle is?
Yeah.
How are you supposed to find out?
How are you supposed to find out?
Just enough by what kind of structure?
How do you find out? You use VSEPR. VSEPR to find. And so for VSEPR, here, what would the ideal angle for ammonia be? The H and H angle. 109. But because of the lone pair on top, it's going to distort this angle a little bit. How much does it distort it by? 2. So it would be about 107. What was the other distorted angle that I showed? The other distorted angle was for this guy here. Let's just build it. Submit that for calculation. Give this a minute to start it up here. You recognize this one? Ooh, water. What's the ideal angle in water? 109, but there are 2 lone pairs here. 2 lone pairs, each lone pair should distort it by 2. So we're going to draw from 109 to 105. So the only scenarios were 1 lone pair, 2 degree, 2 lone pairs, 4 degree. Now, we could have a, in fact this should show the angles too. And we can get the angles from this. Measure angle. Do you see the angle here? I guess you can't see the angle there because the screen is cut off. Show you the angle. Yeah, I just lost the angle. You see the angle? 104. This is a guess. I'm going to guesstimate. How about this molecule here? What did we say the angle is going to be? 107. 106.36 angle. Off a little bit, but what's this one? This is the quantum mechanical calculated angle. The actual angle in ammonia is closer to 107. And the actual angle in water is closer to and so let's take a look at this really quickly. Bond angle for NH3. What do they say here? They're saying 107. But I don't know if that's the guessing, like we're guessing, or is that the actual? I want the experimental. So this is probably, they're doing the exact same thing we're doing, guessing 107. And so let's look at the experimental bond angle, which is the real bond angle for it. What is the experimental bond angle for ammonia? You see, they're saying 107. This is due to the repulsions, but that sounds like the guesstimated bond angle. Well, anyway, it's close to 107. What is the, oh, here it is, 106.8. So 106, oh, here, 107.29. Let's see. This is for solid. Oh, this is the ab initio calculations. Ab initio's quantum mechanical calculations. Shoot. That's not what I want to do then. It doesn't matter. So it's just a guess, you know, I'm just saying around. And the same thing with water, you know, it's a guess. What do they say the bond angle for water is? See what they put for water? 105 or 104.5. There's only one other molecule that you would encounter where I would ask you the distorted bond angle. We covered it. CHO. You know what CHO is? CH2O. CH2O, this should have a bond angle of what? 120. But the HCH angle is going to be compressed to about what? The OCH angle should be expanded or compressed. In other words, is the OCO angle going to be greater than 120 or less than 120? OCO angle. Well, the thing is, it's this. We're looking at pairs of electrons. So here we have one bonding pair, but here we have two bonding pairs. If we have two bonding pairs, is it going to take more space or less space? More space, which means this angle should be expanded, this angle should be contracted. About how much should this be expanded by? Well, one extra pair means about 2 degrees. So this should grow to about 122. And this one should grow to about 122. And then this one should shrink to about 116. And so I don't have the experimental data, but let's go ahead and do a quantum mechanical calculation. You want to see how fast quantum mechanical calculations are? It depends on how sophisticated of a calculation you want. And so to build the molecule is pretty easy. This is how you build the molecule using Spartan. That's pretty easy. And then we're just going to submit this for quantum mechanics quantum mechanical calculation has started. This is an i7 computer. So we gotta wait for the calculation to finish. When I did, what did I do? When I was at UCLA, I did ethanol, I think, and that took over 24 hours of computing calculation. This was fast. Do you see how quick that was? It took less than a minute. It's done. So this is the geometry. It's calculated, you know, what the optimum bond angle is. So let's go ahead and take a look at the angle here. The OCH angle is, can you see that? It's 122. And that means the HCH angle is 115.5 or 116. And so we're just using these as ballpark guesstimation. You know, just one lone pair is going to lead to about a 2-degree distortion in the bond angle. And it's better than just calling it 120, 120, and 120. You know, if we can kind of guesstimate where it is a little more precisely. And so what types of molecules are you going to encounter? You're going to encounter water or water-like substances. What do I mean by water-like substance? What I mean by water-like substance is this. Let's build some other one. Actually, we don't have to build everything. Spartan has a library here. Let's do G. Actually, should we do G? No, let's not do that. Let's do this. Spartan has a library of this. You know what this is? This is amino acid. I'm going to submit this amino acid for calculation. Is this amino acid? This is not complete. Shoot. Not right. Sorry. Let me fix this because the new build. Let's go ahead and just build a new one. Okay, this is amino acid here. Let's go ahead and submit this. It's called glycine. This is the one we did. Remember? Did this one. I'm going to put everything in a plane. This needs to rotate a little bit in the plane here. This is glycine. So we just did all three scenarios that you're going to encounter. While this is calculating, what does this look like to you? Well, what this looks like to me, this looks like water. What do I expect the angle to be about? The ideal angle should be 109, but there are two lone pairs here, and it's going to be distorted to about 105. This looks like what we just looked at. You know, this ideal angle is 120, but this should be distorted to about 122. This one's going to be about 1. This one's going to be about 1. This one's like ammonia here. This ideal angle is 109, but distorted angle should be about 107. So those are the only three scenarios that we encountered. Those are the three scenarios that we talked about. However, if this distorted angle's too much, you know, and your let's say your memory is full and you don't have any more room, then just know the ideal angle. That's where most of the points are. The distorted angles are more bonus than you got to know the ideals for sure. 109, 120, 109, that kind of thing. And need to know the ideal angles. And then if you can do the distorted angles, wow, that's extra. Has this finished calculating? It hasn't. This is still calculating. Pending, do you see? Pending. This is giving this computer more trouble. The bigger molecule. So, since they're giving it more trouble, maybe we should have simplified it, made it a little easier for it to calculate. So I completed the glycine. Now what we could do is we could do the angles once it's finished the calculation. So let's just take a look at the angles really quick. Angle should, what did we guess the angle is? 105. What is the angle that's shown here? 105. It's hard to see in the back. What did we guess this angle is? What is the angle? 120. Well, we're off. What was this one? We guessed 122. It was 120. This one? 120. 120, 120, 120. Let's figure out this angle, though. 40. 42.71? Is that right? Let's try this one. Oh, no wonder it didn't finish the calculation. That's why. It wasn't finished calculating. All right, now it finished the calculation. Sorry. Let's go ahead and measure the angle. This one we predicted as 107. What did it come out to? 105. It's this bulky group here. This bulky group, this is called steric hindrance. You'll learn about this in organic chemistry, but this is kind of bulky here, and so it can't really push in so much because of the steric hindrance. These atoms get in the way of each other here. Do you see that? And so if this were just a hydrogen, then it's easy to push in. So we predicted a 107 angle, and it came out to the 105 angle, that one. Let's see this angle here. This one came out to 109 angle because of that bulkiness. This one came out to a 125 angle because of the bulkiness. You see? And so these are called steric factors. The steric factors are going to distort the molecules as well. This came out to 112 angle, which means that when we're guessing, we really are guessing, Of course, the simpler molecules are going to work nicely. This should probably work out okay. This did 106.54, 107. Oh no, that's off too. That's off because of this big, And so in organic chemistry, then you got to worry about these things as well. Steric hindrance. Okay. All right. So, these. Or just a guess, but you can just ballpark guess. That's okay. I'm not going to put too much weight on those numbers. All right, what else? Are there any other questions?
On the exam, are we given a chart that shows like electronegativity of different atoms?
I'm not going to give you the chart because it takes up too much space. I'll tell you what the electronegativities are. Like I'll say the electronegativity carbon is 2.6. The electronegativity hydrogen is 2.2. So the electronegativities for individual atoms will be given. Those would be the Paulings, what we call the Paulings electronegativities. There are a whole bunch of electronegativities out there. Actually, we don't need to get into it. This is the Paulings. We deal with them. In addition to Pauling, there's Mulliken, Allred, Sanderson, Allen. They're different here. These are the Allen values. So the actual numbers would be given if you need them. Okay, other questions on them?
Are we gonna do the audit tomorrow?
I'm sorry?
Are we gonna review audit tomorrow?
Well, eventually, we can review if there are more questions. I need to cover I need to finish up the chapter we were working on. And do some calculations there, so, if we have time. But if we run out of questions, then I need to lecture and those and stuff.
Also, chapter 15 is gonna be on this.
Chapter 15 is not going to be on the test, but I want to finish up chapter 15 this week so we don't fall too far behind. Other questions?
So, like, pressure fractions and stuff won't be on the test, and the boxes that we learned about with the stuff.
Pressure fractions will be on the test, because pressure fractions is chapter 14. But we can, are pressure fractions giving you some pause? I mean,
Not really, a little, but not bad. I just wanted to know.
well, okay. If we look at air, what's the mole fraction of air? Well, we have mole percentage, and so it's going to be 20% oxygen, 80% nitrogen. These are just keeping the numbers simple. And so the fractions, the mole fraction is 20 out of 100 will be oxygen, 20 out of 100 will be nitrogen. The mole fraction is the same as the volume fraction, which is the same as the pressure fraction. And so all the fractions are the same, so it'll be 20 out of 100, 80 out of 100 for volume, and 20 out of 100 and 80 out of 100 for pressure. All these are the same, so the volume fraction, so if that's 100 liters, 20 liters would be oxygen, 80 liters would be nitrogen. If that's 100 atmospheres, then 20 atmospheres will be oxygen, 80 atmospheres will be nitrogen. Those are the fractions. We also have the decimal. Sometimes we'll do 0.20. This would be 0.20 out of 1 would be oxygen. So it's still a fraction, but it's in decimal form. That's all. So they're all kind of the same thing. Yeah, unfortunately, gas mixtures are going to be on this test, as well as the ideal gas law and gas stoichiometry. This test is there a lot of material on this test? So what did we cover? We covered stoichiometry, limiting reagent, excess reagent, theoretical yield. We covered quantum mechanics, covered Lewis structures, and geometry, and gases again. Gases part 2. So a lot of material on this test, but no chapter 15. If I eliminate chapter 14, then that means the next test is going to have it. Maybe it's a better idea. I'm not sure about the practice test. I don't know. I don't remember what I covered last semester when I taught this. How much of the gas stuff I had on there. So let's take a look really quick at it. I didn't put any gaps on this. Maybe it was a good thing. How far are you guys along on chapter 14? Not? Maybe we could put chapter 14 on the next test if you want to. Yeah? Tell me tomorrow.
Maybe you should make chapter 14 extra credit.
Yeah, that's not gonna happen. Next test will be what, 14, 15, 16, 17?
It's not bad.
That's fine, that's great.
Wait, about 18, 19.
That's perfect.
But they're not those, dude.
Well, think about it. If you're already in chapter 14, then I'll keep it. Chapter 14, though, is not that that hard, yeah. You know, just the thing you got to be able to do is just if you can repeat the stuff I did with air, then you'll be fine for this test. You know, a lot of people just can't do that. They can't repeat it. You know? And then the other little calculations with water, vapor, and that kind of stuff. Any other questions on homework or the test? Okay, then let's just end now.